Alright, in our third video we're going to finish up our discussion of circular motion by considering a very special type of motion, uniform circular motion, also known as UCM for uniform circular motion. This is when an object is traveling in a circle at constant speed. Now, if it's traveling at constant speed, that does not mean it has constant velocity. For instance, you have an object here and it's moving around in a circle, and at this instance right there it has a velocity vector, let's say if it's going counterclockwise, like this. And at some time later on, say over here, it has a velocity vector who's got the same length, but as you can see it doesn't point in the same direction. That means that the velocity vector has changed, and if it has changed, you have acceleration. The acceleration is because the object is not going in a straight line. So it does have acceleration. It has centripetal acceleration. The type of acceleration it does not have is told to you by moving at constant speed. It has no speed changing acceleration. So what that tells us is that there is no tangential acceleration. But very important, it does have centripetal acceleration. So in that case, if you have this type of a problem, you know that there is no tangential component. The total acceleration is just centripetal, and it points to the center circle. Something else you know, the center of the circle here is pointed this way. The center of the circle for this is pointed this way. They don't point in the same direction. That means that the acceleration is not constant. And if the acceleration is not constant, you cannot apply the kinematic equations. This is extremely important. In UCO problems, or UCM problems, you cannot apply kinematic equations. They are invalid. So if you apply them, you will get the problem wrong. Okay? Very, very important fact. Never apply them on uniform circular motion problems. Let's show a concept question, because it turns out some of the stuff that we've been doing is not maybe as unfamiliar as you might think. And here's my concept question. Alright, consider the projectile motion from a previous lesson. So here's a gun, it fires a ball, the ball flies through the air like that, and we're going to consider the ball at position X. And the question is, what type of accelerations does this ball have? Now, previously we just chose to just move the acceleration down like that. And we said, hey, by the way, that's minus 9.8 meters per second squared in the j hat direction. But now I want to consider it in polar form. So my question is this. Does it have tangential acceleration only? B, it only has centripetal acceleration. C, it has both tangential and centripetal acceleration. D, it has neither centripetal nor tangential. Stop the video, think about the problem for a little bit, write your reasoning as to why what you think is true, and then turn on the video and we'll discuss it. Okay, let us take the look at this ball. This ball is following a curved path. Curved path. That says they're centripetal. All curved path problems has centripetal acceleration. So this cannot be correct. This one cannot be correct. Now the question is, does it have tangential? Well, as the ball goes up, its y component of the velocity we know is changing. In fact, when it gets here, its velocity vector is the same along the x, but it has no y part. Here it has the same x part, but it also has a little y. So its velocity vector tangent to the path was bigger. So it is slowing down as it goes on. Speed changing. So it has tangential. Correct answer is C. It is perfectly correct to work a problem by considering tangential and centripetal acceleration, but no one who does physics and knows a lot about physics would do it that way. Why? It doesn't make the problem as easy to solve. It's not that the concept is right or wrong, it's about what makes it easiest to solve. If you do it in this manner, with tangential and centripetal, both tangential and centripetal change. In fact, really neat place is to consider right here. Because when it's right here, we know that the acceleration vector points like that. But that's along the centripetal. So at that point, since the vector only has a component along the radius, then it cannot have any tangential at this point. At this point here, it had both. It had a centripetal pointing in, and it had a tangential coming over. And those two summed to get this red arrow, the total. Over here, the centripetal and the tangential were the same. The centripetal and the total acceleration were the same, and there was no tangential. So these are changing. Neither one of them is constant. But if I worked it in x and y, because it always lies along the y, it was constant, and I could apply the kinematic equations. It's which makes the problem simplest. That's why we choose the particular attacking approach we do. So, some general statements about curvilinear motion in a plane. Our concept question shows that any curved path can be seen every instant as a circular motion, a circle whose radius is the radius of curvature of the trajectory at that particular point. So we could always treat things using this technique. In the case of straight line motion, the radius of curvature happens to be infinity. Well, now hold, if it's infinity, then that would be v squared over infinity, and you'd have no centripetal acceleration. So you just have tangential. In the case of circular motion, the radius of curvature is constant. So it makes it nice. It's v squared over r, and r is constant. But we choose the problem to make the math easiest. We didn't choose it here because in projectile problems it would have made the math harder to perform. We chose the easiest attacking path. So it's important to understand that we use different coordinate systems and often define new quantities to make the math simpler for solving problems. But that doesn't mean that there was new physics. There really are very few physics concepts. Definition of acceleration, definition of velocity, definition of coordinate system. Very few ideas. The rest is about figuring out how to set the problem up in a way that will let us solve the math equations that we have. As we go through, we're going to find that we'll redefine terms and change the way we look at a problem. It's almost never because we couldn't write the physics down. It's almost always because we couldn't solve the math unless we take a particular coordinate system or look for something that doesn't change in the problem. All right, that covers this section on circular motion.